This is the Medical Inventor Podcast, where you can learn about new technologies and research in healthcare that will impact human lives.
We in the frame?
Yeah, I think we are. So you can introduce yourself. So your name is Nikola.
Yeah. Hi, my name is Nikola Prpić. I finished medical school in Zagreb this past summer of 2018. Right now I'm working as an intern at the clinical hospital center Zagreb called Rebro.
I was there 30 minutes ago.
Yeah. I mean, it's the fundamental, it's like the basic hospital for the entire University of Zagreb. I am going to quit. I mean, my internship is gonna run out in about a month. Then I'll get my license, and then I don't really know what I'm gonna do. But
you're gonna save people. You're gonna be a doctor finally.
Yeah, that's what a lot
you're
of
gonna
people
get some
think.
money finally.
Yeah, I hope so. I'm not sure. I'm still thinking about where I'm gonna go into like clinical work and go join a hospital, or maybe do a bit of science. Because science is people as patients have their own sort of problems, and I'm not sure I'm ready to face them in that sort of way. I'm still quite great at like just being in a lab and just coding and being alone and doing science.
As much as I know you, I don't know you so much, but I think that's the perfect path for you actually.
Yeah, there is this possibility in like, and I've been looking at anesthesiology a lot.
That's weird. Like why?
Yeah, there's a hidden branch of neuroscience in anesthesiology, and a lot of anesthesiologists, especially in Croatia, which I'm not really happy about, they don't really get too much into neuroscience. But basically, when you're trying to put someone under during a surgery, you have to do work on their brain. And that's the whole basis of neuroscience in anesthesia, and there was a lot of promising work. I've been reading an article just like 2 days ago about a team of researchers found a specific sort of EEG data that can be nicely correlated with the depth of anesthesia, and this should circumvent some of the problems they currently have with some other EEG-based anesthesia monitoring systems. So, anesthesia does require a lot of physiology and pathophysiology, but it also has a component of neuroscience, which I'm really interested in.
Yeah, neuroscience can be implemented basically in almost every specialty.
Yeah, it can, and especially with
because
the
brain
gut
right?
axis. That, and you're still working with pain, which is sort of pain becomes pain in the brain. It does originate from the peripheral nervous system, but if you don't have a brain, you won't feel pain. So if we're working, that does rhyme, right? If we're working with pain, we gotta talk about the brain, and that's and that pain is a fundamental part of practically every clinical branch.
Okay, so right now you're finishing your work on Rebro.
Yeah.
And then you're planning to go further. You don't know where yet.
Yeah.
So
I'm not sure.
That's great. Okay, so let's start with neural networks. So what are they in biology, neural networks? And what are they in computer science? What's the difference and what's the basics?
So they have different origins and different histories. Neural networks in biology have been known for like hundreds of years. Freud talked about them, Golgi talked about them. It's just basically any network of neurons that sort of communicate, they transport information between each other, and they sort of through that transportation and sort of processing of information, you can get them to do sort of complex stuff. They form the basis of our like higher cognitive skills, or even baser. Everything is in neural networks. And in computation, they are still, from the computational point of view, they come from machine learning. And so in the, I think that was like 70s or 80s.
That was the beginning.
60s. Yeah, that's when machine learning sort of started to become a viable option, because before that there was, I mean, even then there was very little computational power, and machine learning sort of relies on quite a lot of computational stuff.
Yeah, so what was the beginning, the first use case of machine learning in computer science? Was it trying to understand written words, letters, a language?
No, it was just, so machine learning, and basically, I mean, this should be more familiar to people, like regressional models and linear regression, which we have sort of all heard of. I think.
What is that?
I've been in statistics a long time, so to me that's like very basic. But basically you have a set of data, two-dimensional data. So you have paired numbers, and you can sort of plot them on a scatter plot, and then you can approximate a sort of like a line through them. Okay. So once you know one variable, like the x, then you can know the y just by using that sort of line. And that's like linear regression, the process of fitting a line through all that scattered data.
It's like finding vectors?
Yeah, it's sort of like that.
Okay.
You're basically trying to understand the relationship between two variables, I don't know, height and weight. Okay. So you have fat people, you have skinny people, but there is gonna be some sort of connection between height and weight. Smaller people are gonna have less weight. And you're trying to find that line, and then once you do find that line, you can sort of fit some confidence intervals. So you can say, I don't know, I'm 95% sure.
So that's some basic statistics, right?
Yeah.
Okay.
And that's the beginning.
That's the beginning. Okay.
Because fitting that line through there, through all that data, it requires for you to sort of do some complex math. Okay. And that math be overcame using computation. Okay. And once you do get, it's sort of all based on the same principle of trying to fit a model. And in linear regression, that model is like a linear model, like y equals ax plus b. Yeah. And you can do other sorts of models. You can do a quadratic model, you can do whatever. And one of the models you can do is a perceptron. That's like a computational one neuron, where you have a lot of inputs. Mm-hmm. You have something they call a soma, and then you have an axon or an output sort of like variable. And if you take all these...
So neurons in computer science are just a word. They do not really resemble the real neurons. They're just...
They're a concept, and they were inspired by real neurons.
Just inspired, yeah.
Yeah, they were inspired. There's a bit of similarity, but not that much.
Okay, so neurons in computer science, do they have only like, they can fit 0 or 1? Or they have more options, like more paths to go?
It's, you can do both. Okay. So, just like in neuroscience, there's a great misconception that neurons work in zeros and ones. And that's sort of true, because they either send...
In real neuroscience?
Yeah, in real neuroscience. Okay. You have a neuron, and it can send an action potential, or it won't.
But it has different modalities. It can...
But first of all, you can have temporal summations, so it's not the same if someone sends one action potential once a second or 100 times a second. Frequency. Yeah. Or you can have local spatial coding, which says that if you have like 5 axons, you can send. It's not the same which one of these axons sends an action potential, because each of them carries a little bit of information.
Yeah.
So you do have this sort of like 1 or 0 status. However, if you're doing the way body deals with these 1s and 0s, is that it tries to sort of create something that resembles an analog signal through it, because it changes the frequency and it changes the spatial like parameters of all these firings. And in the soma, so if we imagine a neuron has a cell body and it has an axon and it has like the dendrites. Only the axon has this innate property of either firing or not firing.
Yeah.
The whole of soma and
can do
dendrites,
everything.
They
All
can be between 0 and 1. So like between well, basically they can't go. They don't have a real limit of how high their potential can go, but they do have a limit how low, because once they do go through that threshold, they'll set off the axonal hillock, and you'll have an action potential.
So neural networks in computer science are used to build models that can do some special things.
Yeah.
And what are those special things?
So the first big thing that neural networks were used for in computer science was this big problem of vision. Because up until neural networks, the whole sort of like the artificial intelligence and all these buzzwords that we hear today, they were all trying to explicitly state what's what. So basically, if you had, I don't know, a horse.
You have some data, and as a computer, you need to say what does this data resemble.
Yeah, that's right. So if we have a picture of a horse, we have to tell it, so you'll know this is a horse because you'll trace the outline, and this outline has to look like this.
Yeah, but in real life, these outlines are dynamic and not always the same. We as humans can understand the little differences, but the computer looks at pixels. The computers actually see pixels, right?
Yeah.
So we need to train computers to group those pixels and find what are they actually looking for there.
There wasn't really that much of a problem of grouping those pixels. There was a problem of the outline was basically the problem. Because the outline could be small, it could be big, it could be sort of in different shapes. I don't know, a horse could have a head looking left or right or whatever. And then when neural networks came on, you had this sort of ability of not explicitly saying what a horse should look like, but you just show the algorithm, the computer, like, I don't know, 1,000, 2,000, 10,000 pictures of horses, and then it would sort of extract information about what does this make, what does it make a horse, like an abstract of a horse. What's the outline of a horse? What's the abstract sort of
how does it do that? Like in 5 sentences, how does a computer know
what the horse is?
Yeah.
It builds a model. And just like we were trying to do...
and that model is a neural network, right?
So a neural network is basically a family of models. So just like we had like linear regression, and then we could do polynomial regression, we could do, I don't know, other types of regressions. It's a regression family. So we have a couple of functions which we can then sort of try to fit into this data. When we're working with neural networks, they all have quite a large sort of input layer. Then they typically have a hidden layer, and then they have an output layer. And all these layers are comprised of neurons. These neurons talk to each other on the other level. Or you can...
Each layer does one thing.
Yeah, that's the thing.
One layer tries to recognize the outline. The second one looks for patterns?
In the original neural networks, today, yeah.
Okay.
When you're doing like really sophisticated models, yeah. But in the sort of, the whole point of neural networks is you don't really know what they're doing, basically.
So we just build them and we give them data and they do something?
Yeah. And then we take, because we take a huge data set, we take like 60% of this data set.
So we're talking about how much data?
That depends on how complex your data is. So if you're if you're just taking, I don't know, white and black pictures,
it can be a lower number.
Yeah, but if the more complex your data set is, the larger it has to be. So
okay, so human diseases and certain things that machine learning can be used for the future for diagnosis, it will actually take a lot of data because it's a complex system.
In some cases, yeah.
Okay.
Because let's take, okay, so you're working at an ER department.
Okay.
And you're taking in patients. And some patients will be really straightforward. So if you're trying to recognize, I don't know. So even saying that someone has
let's say, for example,
high temperature.
We're looking for septic shock in patients that are staying in the hospital.
Okay, that's a complex problem.
Yeah, it is.
But there are a lot of
they're
problems.
solving that already.
They are. That's because they have huge data sets.
Yeah.
But we can find smaller problems in the hospital and then use smaller data sets for it. So stuff like, I don't know, determining if someone has has blood in their urine. That's not a problem which is hard to solve because it's kind of straightforward. And that's why you have to have a very low, it's yes or no, and you don't have a lot of input for it. So you just take a look at his, I don't know, blood count, and you just take a look at his urine, and then you can sort of figure out. That's why you don't have you don't need a large data set. But if you're doing something like, I don't know, I want to automatically analyze a picture, a chest X-ray. Then you have to have a lot, because each of those pixels is sort of a variable.
So when we train the model with data, is someone training the model manually?
So
like someone needs to say if the answer is good or no, or does the computer?
We again have two approaches, but this is in the sphere of this is called machine learning, and then we have supervised, which demands that a person be there and say, yeah, this is the correct diagnosis, this isn't. And then we have unsupervised methods, which don't really need a signed or a annotated data set. So we can choose. However, neural networks, which are very hyped right now, they belong in the supervised sort of arena, because they do need annotated data sets. So you do have to have, I don't know, 1,000 chest X-rays, and then with each chest X-ray, you have to have a diagnosis. So like, everything's okay with this photo, or you have to have, I don't know, this is pneumonia, or this is cord comp.
So what's more important? Learning from medicine and neuroscience and taking that information and applying it to computer science to build better models? Or using computer science models to help medicine by increasing the efficiency of treatments and so on?
That's
like learning from medicine or
learning from computation. I think the best thing would be to combine both. Sure.
Of course.
The thing is, when you're trying to do,
and what do you focus on? Are you focusing on looking how does the brain work and then using that logic to build better models, or are you looking into applying machine learning into medicine?
I'm trying to apply machine learning in medicine. That's because I'm sort of more educated in the medicine sort of field. However, if I have friends, they do machine learning, and when they do have some sort of interesting problem, I do like to jump in and sort of say, well, I think I've seen something in the brain. And
I know your friends, I think. I know.
Yeah,
one guy.
Which one?
From electrocomputational electroengineering faculty.
Which
He's on
one?
3rd year or 4th year.
I got a lot of friends there.
We'll not say the name, but yeah.
Oh, yeah. Well, that's, yeah, I mean, there's a lot of people trying to do machine learning right now. I mean, it's such a trendy sort of like a word, and there's a buzz, sort of like a buzz feeling throughout the field. And that's great because we're finally starting to take hold of all this data that we have, because we've been
accumulating this data is locked. It's not
in
really...
medicine it is.
Yeah, it's like we can't get to the data. How are we going to get to the data? Do you have an idea? I know.
Yeah, I mean, yeah, you could do...
We create data marketplaces.
You could do that, but the thing is, data marketplaces are a great thing to do in like the United States. But when you get to heavily regulated markets like European, the whole thing of like patient data and all this healthcare data which exists in the European Union, it's quite hard to get to it because you have really, really strict laws about accessing this data, and you do have to mostly have an MD diploma.
Yeah, so we'll talk about trading data in maybe a second show, but right now let's go to functional neuroscience. What we wrote that as a point.
So functional neuroscience is a part of neuroscience that tries to decode how the brain works. So I would try to contrast functional neuroscience to something like connectomics.
Okay.
Because the main goal of connectomics is trying to
decode the function.
Yeah, but through connections between neurons. So
you're trying morphologically.
Yeah, more morphologically. However, the thing is that when you get to like really low level, like to individual spines on
that's
axons,
why in the last show we talked about using nanotechnology for diagnosing and monitoring these things. So you can actually track a single neuron through time.
Yeah, you can. But the thing is, you have to track stuff that's smaller than a neuron.
That's we can also do that with nanotechnology.
Yeah, you can, but you get such an incredible amount of data that we don't really know how to even comprehend it, and we still haven't.
Like, what is this?
Well, we haven't described well these sort of like spines and how synapses are formed in the brain and what's there. So we don't really know how these synapses work and how they behave.
So what do we do with connectomics then?
So the main goal of connectomics would be to study all these synapses and all these connections between neurons, and then they say that if you knew all the connections between neurons in the whole brain, you'd know how the brain works. Which to me isn't really that sure, but okay. The other side of that would be functional neuroscience.
Okay.
So they say that connections, they both borrow from each other, but functional neuroscience sort of tends to lean more on which areas of the brain activate which axons fire, which is what neurons are activated when we are doing, I don't know, when we're walking, when we're moving our hands, when we're planning action or whatever. So those are the sort of the two sides of neuroscience, and I think there's a way to combine them, and that's through like sort of network science and graph topology and stuff like that. There's a way to connect this, just the activation of neurons and the connections between neurons, and then you can sort of have a broader, more abstract understanding of what brain networks are. Because brain networks aren't the same as like neural networks. Neural networks are networks between neurons. Yeah, and they're models in computation. In biology, they're just networks between neurons. But when we're talking about brain networks,
then different systems talking inside the brain to each other at different times.
It's sort of like a whole new level. When we're talking about neural networks, then we're talking about like small stuff.
That's like people, and this is like states, governments, companies.
Yeah, that's basically brain networks, and there's a lot of knowledge and a lot of good ideas and good ways of thinking about networks that come from computational sciences and from, I don't know, information theory. And there are some groups in neuroscience that are using this knowledge, but most of neuroscience and most of brain philosophy and mind theory hasn't really taken advantage of all this knowledge that exists about how networks deal with information flow, and how they process this information.
Okay, so networks, from abstract to concrete.
Yeah, so when we're talking about networks, and when we were talking about these models of neural networks, we were talking about something that's very abstract, which doesn't really exist in a computer. So when we're trying to build a model using neural networks, we're not actually taking neurons and putting them on chips.
What we talked before, yeah.
We still have a regular processor, which is based
But do we need to change
transistors.
Completely the technology that's used today to be able to do even better models? Because right now we have silicon chips, we have 0 1s. Maybe we need a biological computer. Maybe we need quantum computers to have it.
Yeah. Neuromorphic computing exists. It's still sort of in its infancy. There's only a couple companies that are doing it. They are doing stuff which is helping develop neural networks. The thing is, neural networks aren't really designed to work with silicon neurons.
They're not.
Because the whole model of a neural network basically comes down to solving differential equations. And when we already have some algorithms that are quite good at it, and those algorithms work best at graphical units. So any graphical unit GPU, which you have in your PC, probably at home, is great.
I don't have a PC, I have a laptop.
Yeah, I think, and you have a Mac, and I think your Mac has.
It doesn't have.
It doesn't have a GPU. Okay, so someone else, your friends that have PCs.
I have a GPU that I use for gaming.
Yeah.
I know a few friends that are have 30 GPUs, but they're mining some crypto with that.
And you can use those GPUs great if you want to do
repetitive tasks.
Yeah, repetitive tasks, and if you want to do something like neural networks. Okay. Because you got to do a lot of parallel computing in neural networks. So basically right now, the problem with neural network models, if there is a problem, isn't really with the computational framework not being like neurons. The problem lies in something in data and the way we gather data.
Okay, so we are back. We're back.
Yeah. So we're back. So deep learning and machine learning. Deep learning sort of refers to deep neural networks, which are just, so as I was saying, there's an input layer, hidden layer, and then an output layer.
Okay.
If you have more than one, and then you have a lot of these hidden layers, then you're talking about deep neural networks. And the thing is, they are quite computationally heavy because all of these neurons are talking to each other, and you have to get through to the basis
when
of
these
how
things start working.
Yeah, they work.
We will know. It's crazy, man.
Yeah, it's quite interesting, but doing sort of sophisticated deep learning is something on a next level. So it's great to implement it, and
we'll be just taking data, being data junkies, and putting it inside and trying to learn more stuff.
Yeah, but for this, so you have to have someone that does neural networks, machine learning and stuff. This has to be someone that's a computer scientist that has a really good background in computation. However, and you have to have professionals, something like doctors, which are working with patients, and they're giving you the data. However, there has to be a person in the middle of those two, because the computation science guy, he ain't gonna understand he's not gonna understand the doctor, and the doctor, he doesn't know enough about computation to tell him about what he can extract from all this data. So you have to have something like a biomedical statistician or something like that.
Interdisciplinary.
You have to have something in the middle which can understand the doctors and it can understand computation. So this person, which I'm sort of trying to be, and I'm trying to encourage other people to be.
Good job for that, man.
Thanks. Which I'm trying to encourage other people to be. This is someone who has to understand a bit about biology and a bit about computation. And then when they do get into biology, they have to be capable of going deep into this field, whichever field they choose, and they have to be able to to understand and to explain to the computational team, person, whatever, the whole
I'm looking for
company.
this, let's do it like this.
And that's something we really, really lack, because if you're looking at like our elementary education, we have math, we have languages, and we have sciences.
Boxes, and new things are not born out of boxes.
I mean,
it's a totally new box that needs to be developed.
And we have to talk about
we need to take a little bit from this box, a little bit from that box, and then we create something new. That's why interdisciplinary professions are always the most important thing when we are advancing new technologies.
They are. The thing is, we can't really, we're not talking about data in our elementary education. We do talk about math. And then most people, when they talk about numbers, they think they're talking about data. They're not. Data is separate from just numbers. So like 1 in math can be 1 whatever. It can be 1 apple, or it can be 1 turtle, or it can be 1, I don't know, building. However, when you're collecting
data... It's language for data.
Data has sort of an added complexity above those numbers. And talking about data and data science should be something we're talking about from elementary school all the way through high school, through higher education. We have to like revolutionize everything, because the way we're using data science right now, we're using it everywhere. We're using it in, I don't know, in fashion, in science, in art, in medicine. Every single area of human activity is being impacted by data.
Okay. So we have reinforcement learning. Subthalamic nucleus.
So reinforcement learning is it's a concept that was also taken from machine learning. It's sort of a different way. It's once again, you're building a model. So you're trying to understand, you're trying to model behavior in a way to predict whether your object is going to make choice A or choice B, just by observing your object. Okay? And it's a complex algorithm, whatever.
What's an example for that?
So you have, I don't know, a mouse, and he's going through a labyrinth, and it has a couple of... it has cheese, and it has, I don't know, an electric shock.
Okay.
So you have like positive reinforcement, and you have negative reinforcement. And you're trying to model his behavior. So you're trying to determine or predict whether he's going to get to the cheese or to the electric shock, and how fast he's going to learn where the cheese is, and how fast he's going to learn where the shock is.
Does he use the does he use the frontal cortex for that?
In part. He uses mostly his limbic cortex, because the shock and the cheese, they're both
I know for humans this part of learning, it's really heavily involved. It involves the prefrontal cortex. It gets
the planning phase does. However, the sort of
even the learning phase. I was reading a research. It's
I mean, the learning part, it does involve some areas of prefrontal cortex.
You actually get smarter when you get unexpected rewards as a human?
Sure. I mean, it depends on what the researcher's question was and what he was trying to study. However, the thing about reinforcement learning and the subthalamic nucleuses is that it really nicely connects machine learning models and biology, because there's a proof that we do use reinforcement learning, which is a completely abstract model which was developed.
So it works by rewarding. So the limbic system detects some fears and some pain.
Sort of.
Yeah.
So you have the dopamine system and the nucleus accumbens septi, and it releases dopamine, blah blah blah. And this dopaminergic
so that changes the neural networks in the brain when we learn. So let's take the mouse.
Okay.
For the example, his brain changes when he learns new things, right?
Sure.
The neural network changes.
Yeah.
It's dynamic.
Yeah.
So how does it change? Like does something really move?
Oh, yeah, it does. So that's like
synapses change. Synapses change, right?
Yeah, they do.
Okay.
So synapses form and then they disappear.
So biological beings can learn.
Yeah.
And change synapses, but computers, when they learn,
they also kind of
change synapses.
Change synapses.
Like by themselves, or I code something and I change it.
But so you code.
I need to build a model. I need to build a model that will change it automatically.
Building a model means coding this sort of.
But I do it once.
Yeah, you do it once and then you start it. But the thing is, this model that you're building, it's sort of an iterative, program.
So how does
it runs on and on and on.
Yeah.
And you write a small piece of code which just runs for forever, and then it accumulates knowledge.
How does a computer know if his answer is good or bad? Like when he tries to learn something new.
Well, because
does it only give out a percentage? Like I'm 95% sure that this is this, or does it?
Yeah, but you have to ask yourself about how does he know that he's 95% sure? And that's the question. Where you get to supervised learning and the whole annotated data set that I was talking about. Yeah. So you have to have.
But humans don't think like this. Like I'm a mouse. I'm going through the labyrinth. I think it's 95% that I need to go left.
The thing is,
I just feel it. I just know it, right?
Yeah, you think that, but then you feel it. So.
But does our brain also work like that? Like it's 95% that this is true, and then I choose that, but I don't know that I'm thinking like that, or is it?
It kind of is.
Or is it deterministic?
The way we're currently studying the brain. It's probabilistic. So our brains,
it really is like that.
Yeah,
so it's quantum.
It depends on what you mean when you say quantum. I mean,
I don't know, like.
It's Bayesian. It's probabilistic. It's sort of, it thinks in terms of there's an 80% chance that there's gonna be a bear there, and there's 20% chance that it won't. But the whole sort of feel of Bayesian statistics and it's specifically like prediction coding, which is going on in the brain, constantly thinks about building these probability models, and that's how we are currently thinking and understanding the brain.
Okay, so child development and neural networks. So we have a child, it's growing up.
So when we're looking at children and when we're looking at training of neural networks, there's a lot of similarities. Neural networks.
Only human children or any animal?
Any animal.
Really?
Because the thing is, every living creature is constantly trying to associate different stuff. That's the basis of the whole learning process. Whenever we're talking about learning at the basic sense. We're talking about sort of Hebbian learning, and there are problems with Hebbian learning. I'll say that like right now. But the sort of the basic premise that neurons that fire together wire together. So if I see, I don't know, a horse and I see it in a circus, there's a connection that
not at the same time, but
that's like created there.
Close.
Yeah. So now each time when I see a circus, I'll be thinking, ooh, is there a horse? Where's the horse? So this is the sort of how you start to learn anything, even as a child. A child learns that
association.
Association.
Yeah.
Association is the basic principle behind all learning.
You smell something and then you immediately remember what it is.
Yeah, and neural networks associate, and they do it quite well. And they really, and the whole sort of area of machine learning also depends quite heavily on associations, on the abstract sort of associations. So
for children?
Yeah, so as far as I've been looking at both child neurosystem development and their psychological development and neural network training, there's a lot of similarities. And that's the thing that sort of...
So children are basically little computers that are...
Children are like basically little neural networks.
Yeah.
And
that's basically the only thing they are. They have a big head. They're just a neural network that's trying to become better.
Because when we're talking about adult people, we can't really talk about initializing a neural network. So when you have a neural network, the way you train it is that you first pump in sort of random data, and then you give it real data, which then sort of trains it and makes it become the machine that you're trying to build.
You make it dirty.
Yeah, you basically do, like, you do it randomly, and then you try to sort of put in some sort of knowledge into the...
Structured data, right?
Structure.
Okay.
However, when you're talking about adult humans, you can't really have a random, like a blank slate. Let's say
you're already trained.
Yeah, because you're already... However, children, when they do, like, leave the womb and when they're created, when their brains are sort of mature, they are literally blank slates. They can see, because so when a baby first leaves the womb and it's born,
he sees, but he doesn't know what he's seeing.
And the thing is, it's sort of gathering all these inputs and all this information, which is coming into its through its eyes to the brain, but it can't really make sense of it. Neither can it from hearing or taste or any of the other senses. And then it sort of tries and builds models on it. So when you're talking about children, like the first few seconds after they're born,
they're using association, rewards, pain points, and they're looking at what's...
And the interesting thing is you can transfer all this that we're talking about to something like, I don't know, psychoanalysis, which is I just said that, and that's incredibly unpopular to say, because nobody...
It's not unpopular if you're saying it.
I tried to do like...
It's unpopular maybe in other circles, but
I tried to do like a poster on a sort of like a computational biology conference, and it was entitled Neuropsychoanalysis, and it was trying to... No, computing neuropsychoanalysis. So I was trying to take... not that really. I was trying to take computational neuroscience, and I was trying to build it into neuropsychoanalysis, because psychoanalysis is like 100 years old, and it's mostly theories. And then people came and they tried to understand what's going on behind psychoanalysis by putting parts of the brain, like associating brain regions with certain psychoanalytic terms or abstract ideas. And then we still haven't gotten to like the 21st century where we're trying to use computational neuroscience to understand both the neural aspects and the psychological aspect of psychoanalysis. And that is hugely unpopular.
But it's important.
I think it's useful. I'm not sure. Yeah,
I think it can be useful.
That makes it. Because psychoanalysis is psychotherapy, and you can help people with that.
Yeah.
And if
they learn something and they get a psychological, and they have a psychological problem or a disease, they need to detrain, like they need to reverse the training, right?
Yeah.
How can we do that?
Well, the thing is,
it's already hard-coded inside. The network is built. We can't really.
You know what? At the University College of London, they got to the same point where you're at. So they got to. We have this problem. They're already trained. So how do we untrain them?
Yeah.
And
if you can untrain people, you can train them better, and that's
apparently a great way to untrain people is to give them like magic mushrooms and LSD.
No, it's not funny. That's true.
No. It's really good. That's like. Currently, all these things that
everything,
you're hearing,
right?
You sort of reset it.
Yeah.
So you reset it, and then it starts to go back to where it was. However, if you use psychotherapy right at the moment when the whole brain is sort of like going off this trip, like the magic mushroom trip, you can sort of rewire the brain in a right direction, and then you can have like a healthy individual.
Yeah, but still, it can untrain a little bit, but not so much, because like morphologically the neural networks are already there. Like
the thing is the way we're thinking about
with these drugs you can only change neurohormones and molecules.
Yeah, but the thing is they're basically the same, because when you're trying to unlearn something, in most cases, you're not trying to restructure the brain.
It's only molecules.
You're trying to accentuate some parts of this structure.
Okay.
So you want to try and give just enough neuro.
Yeah, like give out more or reduce it.
Yeah,
I get it.
To some parts, and you can do that with drugs.
Yeah.
So
and change receptors, right?
Yeah, you're trying to. So if you have like a structure that looks like it's 3D and it's really complex, you're trying to take one line of this complex network and you're trying to strengthen it. And let's say that this line is a positive sort of trait that
so
someone is.
If you're building a computer model for machine learning and you don't build it well, you can give it mushrooms to retrain it to the computer.
Yeah, I mean, the thing is...
I'm joking, you can't.
Giving mushrooms to the computer is really, really easy. You just have to like insert some sort of fuzziness in a hidden layer, and that's basically giving it
fuzziness.
Mushrooms. Yeah, fuzziness is like, you're giving just a bit of randomness to each weight. So you're being...
and by the way, you didn't explain what are weights, can you...
Oh, weights are... between all these hidden layers and the input and the output layer, we have connections between neurons, and these connections, their property is weight. So you can basically think of all these connections as sort of weights, or how strongly does one neuron impact another. That's weight. So
we insert the fuzziness.
So when you're inserting fuzziness, you're just sort of you take
random
a bit
data,
of,
right?
It doesn't necessarily have to be data. You can just take some sort of like a random number and add it to all of these weights, and you'll get this sort of fuzziness. So you'll change the whole behavior of this neural network, and it will start to at first it will give you bad results, but then it can, if you're giving it right data all the time, it can sort of correct itself. It can correct something that it was wrongly trained on.
Okay, that's interesting. Okay. Yeah. So Human Brain Project, and what about that? Like,
the Human Brain Project, that's where that's the conference where I was trying to give this paper. It's a great project. It's unfortunately right now in its ending stages because it lasted for 10 years, I think, from 2010 to 2020. And it's like 2019.
One more year.
They took in about like €1 billion to just study the brain, and their goal was
Did we learn anything with that?
Yeah, we did a lot of stuff. I mean, the thing is, the €1 billion were sort of spread out to, I don't know, 150 universities all across Europe, and they use this money to like build computational centers and biological centers, blah blah. The thing is, the Human Brain Project is the best, currently the best thing I've seen in trying to connect biology and computation. The whole point of the Human Brain Project is to create models of brains. So like the fruit fly brain, the mouse brain, and the human brain. They're trying to build...
In computers?
Yeah.
Digital brains?
That's sort of the goal. They haven't really done it with the human and the mouse brain. They're doing like really, really promising work with the fruit fly brain. Yeah, fruit flies.
So we basically transferred brains to the chip already?
Well, we've done that in like 2004 when it was transferred the C. elegans, which is like the first model that was transferred from, but it didn't really, there's a lot of challenges with doing
that's what I'm saying.
Brains to chips, but...
so how long will it take us to transfer our brain to the chip, the human brain?
Oh, that's a really great question. Well, I think...
5 years.
Oh no, like a lot more. Like
you sure?
Yeah, and by like 21.
Maybe we can already do that.
Well, you need it. Sort of, it depends on how you define what does it mean to transfer a brain to a chip. But I think like the full-on experience of having a complete human personality, like a person in a computer, I think we'll have to wait another 80 years for that.
80?
80, yeah. Like 2100. I think if we do it by 2100, I think I'd be...
Let's try to be healthy and stay alive by that time.
I'll try, but I'm not sure I'll be able to. But I think, by 2100, I think we can have like the first human brain in a chip, which means we'll be immortal, basically. And which will be great. I think I'd love to be immortal.
Did you watch the series Altered Carbon?
Yeah, I did. That's a great series.
Yeah.
I think that's gonna
like cloud backup for your consciousness.
Yeah, I mean there's no reason why you couldn't do that. I think that robotics are gonna be quite a bit in front of our consciousness research.
What?
Yeah, I think we'll be I think humanoid robots are like 20, maybe 30 years away. Because we already have good silicon skin, good motors, everything.
But coordination for robotics is really bad.
Is improving.
Is improving, but that's the hardest thing, actually.
Yeah, but have you seen like the Boston Dynamics group and the Atlas run and do parkour? And it was like, it's really impressive.
Yeah,
and if you
but that's the hardest thing in robots, right? It's easier to make a smart robot, like to understand text, than to someone that has like fine hand movements.
Yeah, I mean...
Like we as humans are really good at fine movements.
Yeah, we are.
Really good. That's why we're humans, basically.
Yeah, but
because of the thumb and everything.
We're not good at like repetitive fine movements. That's not something we're great at. Because
if you
take any industrial robot, it can do repetitive tasks faster and for longer than any human. We are sort of more creative and we're more flexible and we have other things going for
something as a surgeon will definitely stay for a long time. Because it needs to be
but that's not the technological thing. That's not because of technology. The technology to have a surgical robot is already here. So we have like the Leonardo da Vinci robot is really good at operating. And if we just had the required AI, so we just we're just missing the software
just
part.
missing
yeah
the
but
software.
I mean the hardware part is already here.
Yeah.
And I think that if we're talking about like synthetic humans, the hardware is gonna be there in 20 to 30 years. We'll have synthetic bodies and we'll have everything that's required. However, if we're talking about transferring consciousness to like software, that's where we have to wait another 50 years after we get synthetic bodies.
Yeah.
That's not a near future.
Yeah, okay, I get it. Okay.
Yeah.
Thanks for this great talk.
No problem. Thanks for having me.
I really appreciate your time, and your knowledge is really deep about this topic.
Yeah, but thank you very much.
Okay, great. So, do you want something to add?
Just that everybody really should try and have we're constantly talking about interdisciplinary research. We should be talking about transdisciplinary, because interdisciplinary means if a computational scientist is working with a biologist, what I'm trying to do is translational science. And that's when you have one person which does both computational science and biology. I think that's the future.
And maybe something third also.
Yeah, sure. You can do, I mean, the great thing would be for you to do a bit of everything. Because, jack of all trades and stuff. But I don't know. I mean, let's try and have people do a bit of computation alongside with like medicine, biology, chemistry, physics, whatever.
Okay.